Okay. Hi everyone. So, hi, how are you? Good. Any question? And
I
yes.
had a question. So last week I didn't attend, so
Okay.
the groups are being formed, I believe, I just learned.
Yeah.
So
No. Have you formed teams, guys? So you haven't found a team member. I know what another person who doesn't have any team yet. But you feel free to check the class list
okay.
in the course link, and also I saw that you have a posting. Yeah, use that group also in Teams to find team members, but don't forget to tag the general, for example, so it notifies everyone. Yeah. And also during the break, you can try to find team members. Any other question? No? Hi. So, yeah, please form teams. And if anyone has some cannot find a team, a good team until the deadline, we can. It's okay to submit it a few days after that too, but try not to be too late for that. Okay. So yeah, and after that I will read your proposals and give my feedback to you. So thank you. Let's start. Last time we talked about k-nearest neighbors until the middle. So let me recap what we talked about. So we said first we talked about k-nearest neighbors in general. We said we have a data set of n data points, each of which is d-dimensional, and then we said we can calculate the pairwise Euclidean distances or any kind of distance between them, and then we can sort for each point. We can sort the distances, right? And we take the to ascending. We sort them ascending in ascending order, and then we take the k smallest distances for each point. Therefore, we get the k nearest neighbors of each point, right? As a result, we can have a graph called k nearest neighbors graph or KNN graph, whose vertices are the indices of the points 1 to n, and an edge exists from vertex j to vertex I if xj is one of the k nearest neighbors of xi, right? And we talk using a counter example. We said that this graph is directed because if xi is a k nearest neighbor of xj, not necessarily xj is a k nearest neighbor of xi. It might be, but not necessarily. And we also said that we can have adjacency matrix, which is a matrix whose ijth element is 1 if j is a k nearest neighbor of xi, and not necessarily symmetric for the same reason that we discussed, right? And we also said that if k is much less than n, this adjacency matrix becomes sparse. And also we talked about another variant of adjacency matrix, which is n by k, where rows are corresponding to the points and k are corresponding to the k nearest neighbors. We can also call it k nearest neighbor matrix, by the way. Nearest neighbor matrix or adjacency matrix. Then we talked about how to use KNN for machine learning. We said we can use it for regression or classification. Simply, we use a summary statistics of the labels of the nearest neighbors for every point. And this summary statistics in regression is usually mean, and in classification is usually majority vote, right? Or mode. And we said, so as a result, we don't have any training phase in KNN. We only have a test phase. And then we said that we can have kernel KNN. How? So simply, rather than using Euclidean distance in the input space, let's calculate the distances in the Hilbert space or feature space using this formula that we also proved. And we said that Sholkov has proposed this, and this distance equation 3 in a NeRIPS paper. And we just showed you the proof. The proof is so simple, right? It uses kernel trick. And so we said for calculating the distances, we used the distances in the feature space or Hilbert space, and then we sort the distances as before. It gives us kernel KNN, and we can use it for regression or classification. And then we talked about distance metric learning for large margin nearest neighbor classification. Before that, before talking about that, we talked about generalized Mahalanobis distance, and we had a good discussion there. So I don't go into too much details. Recall or go to the end of the previous session to remember what we talked about. But let me briefly tell you that we said that we have two clouds of points. Assume we have two classes, and we have a x1 and x2, and we have a test data point x, right? And we said Euclidean distance, if we use Euclidean distance of the point x from the means of the two classes, its Euclidean distance says that x belongs to the class 1 because it is shorter distance. However, our visual system says that it must belong to class 2. So we said apparently the covariance or the scatter of the classes need to be considered, and we said Mahalanobis has done that. As a result, he has used sigma inverse for the scale of the distance. But we said that why sigma inverse? Because the more scatter, the shorter the distance should become, the more variance it has. And we also said that this analysis of equation 4 is very important, very important. So what did we say? We said that consider this squared Mahalanobis distance, generalized Mahalanobis distance. We said that Mahalanobis distance uses sigma inverse. Later, people generalized that and replaced the inverse of covariance with some matrix M, which needs to be positive semi-definite to satisfy convexity and triangle inequality, because it's a distance metric, right? It needs to satisfy all of the 4 properties that we discussed for norm in the preliminaries, recall preliminaries. And so one of them was triangle inequality, and for that, this matrix M here or here needs to be positive semi-definite, meaning that its eigenvalues need to be non-negative. Then we said that we can decompose M into LL transpose. Why? We briefly talked about it here. We said consider the eigenvalue decomposition of M. Then we can, am I allowed to write delta as delta half times delta half to the power of half times delta to the power of half? I'm allowed to do that only if all of the elements of delta are non-negative, right? Because if I have a negative elements, then I can't write it as that to the power of half times that to the power of half. Then we said, okay, but we can do that. Why? Because we know that M is positive semi-definite. We just said that. And we know that delta is a diagonal matrix whose diagonal elements are the eigenvalues of M. And as it is positive semi-definite, all of its diagonal elements are non-negative and the rest of the elements are 0, right? So we can do that. So we can decompose it into this. And then if I denote U delta to the power of half as L, I will have LL transpose. As a result, I could decompose M into LL transpose, right? So if I do that, then I can bring the left L to the left side, left parenthesis, and L transpose to the right parenthesis. And I know that a transpose that I have for the left parenthesis reverses the order in the matrix multiplication. So I will have this. What is this? This is a squared L2 norm of L transpose xi minus xj. In other words, what is L transpose xi? It's the linear projection of xi to the column space of L. What is L transpose xj? The same, linear projection of xj to the column space of L. Recall preliminaries. We discussed these in the preliminaries. And then, so this is this. What is it saying? Basically, it's saying that my generalized Mahalanobis distance became squared Euclidean distance. So my squared generalized Mahalanobis distance became squared Euclidean distance, but after some linear projection. So basically, it says that I have some data points in the input space, let me transform them to some other space, and in that space, I use Euclidean distance. It makes sense. Why? Because if you apply that linear projection, what does it do to these clouds of points? Can you tell me? Their variance become equal. So if the variances of the scatters of the classes become equal, then you can simply use Euclidean distance, right? That's the linear projection. What is it? What it is doing, and that's interesting. Okay. So we talked about these. Now, starting this session. So in order to improve the KNN classification performance, we can improve that. We should decrease and increase the intra-class and inter-class variances of data respectively. Do you agree? So when my classes are confused with each other, what can I do to improve classification accuracy? I can make the classes less confused. How do I do that? I have two options. Either I decrease the variances of classes, or I increase the variances between classes, right? Or I do both, right? This is the idea of Fisher. Ronald A. Fisher in the previous century came up with this idea, and it has dominated the supervised dimensionality reduction area. So almost all of the supervised dimensionality reduction algorithms, including supervised deep metric learning, all of them are using this idea. They're decreasing intra-class variances and increasing inter-class variances. So let's do that here too for KNN. So of course, one might say, when I introduce KNN to you, you might be wondering, why are we using Euclidean distance? Who said that? I said you can use any distance, right? Who says that Euclidean distance is the best? We just showed that in the previous slide that it's not always the best. So let's use generalized Mahalanobis distance and find the matrix M for best classification using KNN classification. So this is the idea. And as can be seen in this figure, for example, this is that I'm depicting the idea of decreasing the intra-class variances and increasing the inter-class variances here in this figure. Consider one way to do that is this. We use triplets. One way. So there are several ways to do that. One way, which is very famous, is this, triplets. So we have data sets, right? We need a pre-processing to generate triplets out of this data set. How? So by triplet, I think it's obvious. I mean 3 points. So sets of 3 points. I take 3 points, then 3 points, then 3 points, then 3 points. But what are these 3 points? In each triplet, I have an anchor, I have a positive, and I have a negative. Anchor and positive belong to the same class. Negative belongs to another class. Okay, and I can take them randomly, right? I have a lot different classes. For one triplet, I randomly select one of the classes, and I randomly take 2 points out of this data set, out of the class as anchor and positive, and randomly select another class, and from that random class, I take a random point. It's a negative point. This is a triplet. I do this procedure again and again to generate triplets out of my data set. So whenever I'm using triplets, I need to have a pre-processing step to generate triplets out of my data set. Okay, then you tell me I have a triplet. What should I do? Assume I want to design an algorithm, and my data is a triplet, is in the form of triplet. What should I do for fulfilling that idea of decreasing the intra-class variances and increasing the inter-class variances? Of course, I should what? You're saying, right? No? So I have anchor, positive, negative. Anchor and positive belong to the same class. They should be pushed toward each other, right? Negative is, and anchor and negative are from different classes. They should be pushed away from each other. So basically it's this. If I have anchor, I have positives, I push the positives toward anchor. And if I have negatives, I pull away the negatives from the anchor. So this is the idea of triplet, right? In my deep learning course, I will talk about it, that we have a triplet loss. I think it was proposed by Google. So we have two important loss functions in deep metric learning, not related to this course, but related to the idea that I'm talking about. One of them is contrastive loss. The other one is the triplet loss. Okay. And one of them, contrastive loss, was proposed by Facebook, I believe. Yes. And triplet loss was proposed by Google. So, the idea is this: they have some loss function in deep neural network that does exactly what I told you. It pushes the positives toward anchor and pushes away the negatives from anchor. And how do they do that? Using back. So we have a loss and we minimize this loss for that. But here we are gonna similar idea to triplet loss. So I believe that triplet loss was inspired by this. So this was generally proposed before the era of deep learning. And later they were inspired by this paper and they proposed triplet loss. Okay, that's many of the loss functions in neural networks are inspired by fundamental machine learning. One of them, another one is neighborhood component analysis. Before the flourishing of deep learning, it was proposed by Hinton et al. In NeurIPS for regular machine learning using simple optimization. Later, they brought that as a loss function of neural networks. So that's the thing that it's usually done in machine learning and deep learning. Anyway, so I was saying that let's see the fundamental triplet loss in statistical machine learning. That's the thing. Let YIL, so I'm defining several variables. Let YIL be 1 if the data points of XI and XL are from the same class, and if they are from different classes, it's 0. Okay? And eta ij are also defined that is 1 if xj is one of the k nearest neighbors of xi. Okay, otherwise it's 0. So YIL and eta ij, don't confuse them. Eta says that whether a point is in the k nearest neighbors of the other point. By the way, it's not symmetric necessarily. We talked about it. Eta ij. Y says that whether 2 points are belonging to the same class or not. Okay, don't confuse these two. Now we want to do this idea that I talked about. For that, we can use this. We can have this cost function or loss function, and we minimize it using regular optimization, not deep learning. Okay, using regular optimization. So let's see this loss. First off, what is this notation? So this bracket and bracket plus, I'm defining it here. It's maximum of the input and 0. So whatever comes inside the bracket, it's maximum of this and 0. So basically, if it inside the bracket becomes negative, the output becomes 0. Otherwise, if it is non-negative, it becomes exactly equal to what is input. Okay, it's called a standard hinge loss. We have seen it. I don't know if you have heard of this in this course. I didn't talk about it. We have some activation function in neural networks that's called ReLU activation function. For more information, see my deep learning course. ReLU activation function is that. So basically, this function is this. This is a standard hinge loss. Do you see that? Because whenever it's negative, it becomes 0. Otherwise, it's exactly what it is. So that's one thing. Now, what is this? By the way, this is called triplet loss. The whole thing here is triplet loss, which is also nowadays used in neural networks. Okay. Now let's analyze this. What are they doing? Can you tell me what is this doing? First term. So we know that eta ij is 1 when xj is one of the k nearest neighbors of xi, right? And I'm minimizing this term. What is this? This is generalized Mahalanobis distance, a squared generalized Mahalanobis distance between xi and xj. Minimize it when xj is one of the k nearest neighbors of xi. I think it's obvious. So basically, it's saying that if in terms of pattern, xj is similar to xi, push them toward each other in terms of pattern, right? By the way, I think I forgot to say one thing. Eta ij is 1 if xj is one of the k-nearest neighbors of xi, and also it belongs to the same class. Sorry about that, I forgot to say that. So let me recap. Let me tell you again. Let's just restart from here. Y says that whether 2 points belong to the same class or not. Eta says that whether the 2 points belong to the same class and also they are nearest neighbors of each other. Did you see the difference? Right? 2 points might be from the same class but far away from each other. Still their y will be 1, but their eta will be 0. Eta is 1 if the 2 points belong to the same class and also they are the nearest neighbors of each other. Did you get it? Okay. Now, with this explanation, let's analyze this last function. Can you tell me what the first term is doing? It's saying that if 2 points in terms of pattern are similar to each other, are k-nearest neighbors of each other, and also they belong to the same class, of course, push them toward each other. In other words, they are anchor and positive, and they are also similar in terms of pattern, right? So if 2 points are not nearest neighbors of each other, or they are not, or they are from different classes, this first term becomes 0. We don't care. Agree? Okay. Now, let's go to the other thing. So I have, do you see this summation is triple summation. So I have summation over I, summation over j, and summation over L. Let me close the door. So I have summation over I, over L, j, and over L, and I have eta ij, y minus 1 minus yil. So basically this term, I have it again if xj and xj is one of the k-nearest neighbors of xi, and it is from the same class. Okay. What is 1 minus yil? When is yil 1? Can you tell me? When xi and xl are from the same class. So 1 minus yil is 1 when they are from different classes. So basically, these two terms, what are they saying? So I have xi, xj, xl, right? It says that xj is in the same class as xi and k-nearest neighbor of xi, but xl is from another class. So this is exactly the triplet that we have. xi is the anchor, xj is a positive, xl is a negative. Did you understand what I'm saying? Let me say it again. xi is the anchor, xj is a positive, xl is a negative. Here, I'm defining my triplet in this way, that positive means that it is in the same class, but also is one of the k-nearest neighbors of the anchor. Negative means that from another class, okay? Now, for it's an actual triplet, I mean anchor, positive, negative, this term I have it. Otherwise, this term becomes 0. The second, okay. And now, let's talk about the triplet loss that I showed you. So basically, what is it doing? I think here is. What is it doing? Let's focus on this part now. It's basically saying that yeah. So what is this part doing? Can you tell me? I'm minimizing this part, right? Guys, please focus. I'm minimizing this part. This is a constant. I don't care for now. For now. What is this? I'm minimizing this part. What do I mean? This is the distance, generalized Mahalanobis distance between xi and xj, where xj is the positive of xi, right? So I should decrease their distance. So it makes sense that I have positive behind it. I'm minimizing this cost. However, what is this? This is square generalized Mahalanobis distance of xi and xl, where xl is the negative. So I should increase the distance. I should maximize the distance. As a result, I minimize negative this distance. Minimize minus the cost becomes maximization of that cost. Okay, so that's the thing. Now, what is this +1 doing? It's basically saying that continue. So when does this become 0? This triplet loss? When inside the bracket becomes negative, right? According to the hinge loss that I told you. When does this become negative? When? Because gradually xj is pushed toward xi and xl is pushed away from xi, right? But I don't want to do it forever. I want to stop at some point. When the distance, the difference of distance of xi and xl and distance of xi and xj becomes 1. So basically it's xi, it's xj, it's xl, right? So this is one distance, this is one distance. This distance minus this distance becomes 1, stop it. That's enough for me. So basically this is margin. And you can put another value. They, in this paper, in the original paper, they put 1. Later, when they used that in deep learning, they made it a hyperparameter, margin a hyperparameter. Of course, the larger the margin, the more optimization you need to do, because it goes, it needs more iterations, right? Did you get it so far? So far clear? Okay. Now, so we discussed this loss function completely. By the way, what is C? It's a regular, because it's a regularized cost function. It has 2 terms, so it's a weight between the 2 terms, regularization parameter, hyperparameter. Now, I'm minimizing these, okay? With respect to L or M, doesn't matter, because M is LL transpose, right? I can restate it as this optimization function, optimization problem 6. Why are these 2 optimization problems equivalent? Can you tell me? What is this doing? So basically, what is this? This is exactly this, right? Right? These 2 are equal. What about this? This part is here. And this part is here. Agreed? You understand why, right? According to this, I can write the generalized Mahalanobis distance in 2 ways, either in this way or in this way, right? Don't confuse it, because M is LL transpose. Now, so this term is exactly this term. I'm repeating it. Okay. So C is C here. This eta ij is here. I have also YIL here, 1 minus YIL. Rather than the whole triplet loss, I put zeta IJL, okay? And zeta IJL, I define it as an optimization problem variable, okay? But zeta IJL must be greater than or equal to 0. What does this mean? This constraint is because I replace this triplet loss with eta IJL, and I know that according to the standard hinge loss, it is non-negative, right? The standard hinge loss is maximum of something at 0. It never becomes negative. So I need to add this constraint. It needs to be non-negative. Also, I know that M is, according to what we discussed, needs to be positive semi-definite in generalized Mahalanobis distance, right? Now let's talk about the first constraint. According to the standard hinge loss definition, I know that this becomes in effect when it is non-negative, greater than or equal to 0, right? So let's calculate it. 1 plus xi minus xj m squared, this term, minus xi minus xl m squared, this term, right, is, let me think, is great, yeah, is greater than or equal to, let me think a bit, just give me a sec. Yeah. So when what is my desire? My desire is that it becomes negative, right? As long as it becomes negative, that's enough for me. It becomes negative. Yes, I think now it is right. Yes. So rearrange the terms. What do I get? Bring these two to the other side. It becomes xi minus xj m squared. Sorry. Xi minus xl m squared minus xi minus xj m squared is greater than or equal to 1. Agree? I rearrange the terms. However, I can say, let's tolerate it. So here I'm saying that let's tolerate as long as it is 1 minus some positive value, that's enough. So basically, what do I mean? Rather than less than or equal to 0, I will say less than or equal to eta ijl, where eta ijl is a small positive number. Did you get it? Basically, rather than being too harsh in the standard hinge loss, I say take it easy a bit. That's fine, right? As long as it becomes less than eta ijl, which is close to 0, maybe 0.001. That's enough. Did you get it? That's the thing. As a result, I will have this. So I just proved the first constraint as well. Did you see? It's approximately equivalent to this minimization. Why do I say approximately? Because I'm inserting some eta ijl, which is non-negative, which is a small positive number. I tolerate it if it becomes a small positive number inside the hinge loss, I mean. Then my optimization variables are m and eta ijl. By the way, eta ijl is not one optimization variable. How many optimization variables it is? So it depends on your triplets. How many triplets you have? I goes I, J, and L go on the triplets that you have, right? Why did we convert this optimization problem to this? What is the form of equation 6? Have you heard of semi-definite programming? Optimization problem? No? So semi-definite programming says that it has some standard form. So whenever you have some kind of optimization form like this, so this is inner product. So you usually in semi-definite programming, our optimization variable is a matrix, okay? Is a matrix, not a vector. And then we say, what is this? This is C is a constant matrix, okay? So basically, trace of C transpose X. This is inner product between C and X. Recall preliminaries, inner product in matrices, right? So subject to some optimization, nonlinear inequality, but this is important. The matrix is positive semi-definite, okay? Hence the name semi-definite programming, okay? This is a convex optimization problem and can be solved using any optimization toolbox, such as CVX. There are some optimization toolboxes, and it can be solved efficiently using interior point algorithm that we have talked about in preliminaries, right? You don't need to know in this course how you do interior point algorithm, but for more information, see my optimization course. I have talked about it on YouTube. Okay, so yeah, we can solve it iteratively, but it efficiently, but it is slow. Although it is efficient, but it is slow because it is iterative. Okay. So basically, let's go back to where we were. This became a semi-definite programming problem. Now we can use an optimization toolbox, and we know it's convex, so it has a unique global solution. And as you see, our optimization variable is M, right, which is a matrix, and it is positive semi-definite. At that time, people were very obsessed to write their problems as a semi-definite programming, because at that time, it was a very breakthrough in optimization. And if you could formulate your machine learning algorithm as a semi-definite programming, you could publish in high prestige conferences. Okay, I think they published in NeurIPS. So that's the reason that they did it. Okay. Yes, but it is a slow, as I said. Yeah. Yeah. Okay. So the question is equivalence, approximated equivalence of these two optimization problems. So consider the first term. I'm minimizing this term, right? I'm also minimizing this term. I'm repeating the first term here, right? Plus the second term. This is almost the second term, but rather than this standard hinge loss, this term, I have zeta ijl. Okay. I'll tell you. Did you understand that I replaced this part of standard hinge loss with zeta ija? Did you understand that? No. The reason I will tell you, I replaced that with zeta ija. Now I'm minimizing this second term. So basically it means that I'm minimizing zeta ijl as well, right? So, and I know that zeta ijl is greater than or equal to 0 according to this constraint. So I'm minimizing zeta ijl, but it is non-negative. So what do I mean? It becomes a very small positive number, right? So far clear? Come with me step by step. So zeta ijl is pushed towards 0. Okay. Now consider this constraint. So basically, what is this standard hinge loss doing? It says that I want what is the desire of minimization of the standard hinge loss is that the inside of the bracket becomes 0 or negative, that I stop optimization, right? So basically, whenever it becomes less than or equal to 0 or equal to 0, that's my desire, right? But I'm saying that less than or equal to 0 is too restrictive. Take it easy on the optimization problem. Hence, it is approximation, okay? So I said rather than less than or equal to 0, let it be less than or equal to 0.001. That's fine. A small positive number. I also told you, recall several minutes ago, I told you what? Zeta ijl is a very small positive number. So I can say that rather than less than or equal to 0, let it be less than or equal to zeta ijl. Okay. Now rearrange this inequality. Do you agree that I get this? So this is exactly the first constraint, right? I just proved to you that they are equivalent. Did you get it? Okay, that answer. Any other question? No? Okay. By the way, there is another algorithm in deep dimensionality reduction at the almost the same time that they also formulated their algorithm as a semi-definite programming. Again, as I told you, it was a very high prestige to formulate machine learning algorithms as a semi-definite programming at that time. I think it was around 2005 to 2010 at that time. And that algorithm is called, let me remember. What was it called? Semi-definite embedding, also called maximum variance unfolding. Feel free to Google it later. Okay, maximum variance unfolding or semi-definite embedding. They also formulate their optimization problem as a semi-definite programming. Anyways, that was in parentheses. Okay, so we should solve it using SDP or semi-definite programming. This problem using optimization toolboxes, and it is usually slow because it is iterative. This method is called large margin metric learning for nearest neighbor classification. I think it's obvious why. It's first off, it's classification. I'm using labels, class labels. It's nearest neighbors because I'm using k nearest neighbors, right? And it's metric learning. I talked because we are using generalized Mahalanobis distance, right? It's large margin. Why? Because of what the idea of increasing the interclass variances. So I'm increasing the margin between the classes, right? Hence this name. By the way, I and my co-authors have a paper proposing triplet mining for this algorithm. Because what is triplet mining? So I told you that we can select the triplets randomly, right? You remember? Anchors, positive, negatives. But who said that we must do it randomly? We can do it wisely. We can select the anchors, positive and negatives wisely. What do I mean by wisely? For example, what is the hardest case? Let it be very hard. Well, let we take very hard on the algorithm. What is the hardest triplet? Anchor and positive are supposed to be near each other. If they are very far away from each other, it's hard. Anchor and negative are supposed to be far away from each other. If they are close to each other, it's hard. So we can find hardest cases. For example, we can take farthest positive, nearest negative. Or we can go the other way around. We can take the easy case. Nearest positive, farthest negative. So we can have different cases. That's called triplet mining. And this has been used in deep learning for triplet class. But we said, why don't we use it for this algorithm? Because this algorithm is also used in triplet class. So we propose triplet mining for this algorithm, and it's called acceleration of large margin metric learning for nearest neighbor classification using triplet mining and stratified sampling. Okay. Reference 11. And these are the references. Any question? No? Okay. Let's go to the next topic. The next topic is Bayes and naive Bayes. As you see, we are covering these days, we are covering fundamental classification algorithms. We covered regression. Now we are covering fundamental classification algorithms. So Bayes and naive Bayes classifiers. First, let's talk about Bayes classifier. According to the Bayes rule, right? The posterior is this. So what is this? This is probability, conditional probability of where X belongs to the class Cj, right? Cj is one of the classes. Given the data. So given the data X, how much it is probable for that data to be in the class Cj? This is called posterior. It is equivalent to the probability of X given X given that X belongs to the class. So given that if my data belongs to the class Cj, what is the probability of my data? So this is the other way around. Okay, that's called likelihood. Also called class conditional. Times, what is this? This is probability of X belonging to the class Cj. So it's prior of the class Cj, of class, prior of class. Okay. What is this? This is prior of data X. Okay. The proof is so simple because the numerator is equivalent to, because P of X given C times P of C is equal to joint probability of X and C. Okay. Also multiply this with the denominator. That's the same. P of X given C, P of C given X times P of X is again joint probability of C and X, or X and C, doesn't matter. The order doesn't matter, right? So basically it's saying that the proof is this. Joint probability of X and C equals joint probability of X and C. Okay. So simple. The proof is so simple that when I heard that when Bayes came up with this formula, he put it away. He said, it's not worth mentioning that to the world at the first time. So simple, right? Okay, so we can restate it in this way. the likelihood, I can say it as denoted by f of xj prior of the class, let it be pi of j. And by the way, I can marginalize that. Do you remember recall preliminaries? We talked about it. I can say P of X, I can say it's summation of P of X given C, but times probability of all of the classes, right? I should sum over all of the classes. This is called marginalization. Okay. See that this is the cardinality of the number of classes. So the number of classes is denoted by this. Okay. By the way, in Bayes, these words have been borrowed from philosophy. Posterior, likelihood, prior. These are Latin words. So we have in Latin, we have a priori, we have a posteriori, right? These have come from philosophy because at that time, I don't know if do you know the history of language of the science? Do you know all of this? At the time of I think it was at the time of Renaissance, and at around that time, the language of the science was Latin. A bit before that, in the dark ages of Europe, the language of science was Arabic. Okay, but a bit after that, at the time of Renaissance, the language of science became Latin. A bit after that, it became German, and because Austria was the main. So because before that, Baghdad was the main part of the science. Later, Austria. Did you know that Austria was a very famous part of the scientific world? It had a lot of philosophers there. Austria and also Germany. So later, German became the language of science, especially at the time of Einstein and Freud, right? Then later, English became the dominant language of the science. So this is how science has had different languages. Okay, so posterior likelihood, as I told you, prior. By the way, for more information on a posteriori and a priori in philosophy, feel free to read about Kant, Immanuel Kant. He has talked about these things. So by the way, what is Bayes classifier now? So we talked about Bayes rule. Now, what does Bayes classifier do? It maximizes the posteriors of the classes. I think it makes sense, right? So basically it says that for a given X, how do I estimate its class denoted by C hat? How do I estimate? So I have the posteriors. So I say, given this X that I have, what is the probability that it belongs to class 1? What is the probability that it belongs to class 2, to class 3, until all of the classes, right? So I have a bunch of probabilities. Which one is the maximum? It means that that point belongs to that class. I think it's so obvious that it seems ridiculous, right? However, the problem is calculating this posterior. How do we calculate this posterior? It's hard. Okay. So this ridiculous formula is Bayes classifier, and it's not ridiculous. It seems ridiculous. Actually, if you can calculate the posterior, if you can calculate it, this is the best classifier. I think it's obvious. This is the best classifier because no one, because of being ridiculous, it's the best classifier. No one can beat that. It's argmax, right? So according to equation 1 and the Bayes rule, we can say that the posterior is proportional to the likelihood times prior. I can get rid of or ignore the denominator. Why? Because the denominator doesn't have the class in it. For all of the classes, the denominator is the same. So get rid of that, right? Or in other words, multiply all of the probabilities by the prior of the data. It goes away. So I can say this, use equation 3 rather than posterior. Yeah, and the denominator, as I said, is not dependent on the classes. Now, so we had these, I'm repeating them. According to the equation 3, which is this, the posterior can be written in terms of likelihood times prior. So basically, I can have equation 4 for the Bayes rule. The likelihood times prior. By the way, what is this prior doing? Why is it important? What is the difference between prior and likelihood? If you go to sometimes in interviews of industry for machine learning jobs, they ask this question. What is the difference? As you see, the posterior has prior in it. So prior times likelihood. The prior especially plays an important role when we have imbalanced classes, right? Because a good estimate of the prior is the cardinality of that class over the cardinality of data, the number of data points, right? So it takes care of being imbalanced in the population of the classes. And Bayes classifier does not make any assumption on the posterior, prior, and likelihood. It's general, right? Unlike LDA and QDA, which assume unimodal Gaussian distribution for the likelihood. Do you remember? We talked about it. Therefore, we can say the difference of Bayes and QDA is in the assumption of unimodal Gaussian distribution for the likelihood. Do you remember? This prior times the likelihood was also used in QDA and LDA, where LDA was assumed to be unimodal Gaussian distribution. The likelihood. So, but here Bayes is general. Hence, if now it's a good hence. Hence, if likelihoods are already unimodal Gaussian, the Bayes classifier reduces to QDA. Right? Also, if the likelihoods are already Gaussian and the covariance matrices are already equal, then the Bayes classifier reduces to LDA. Right? Interesting. Bayes classifier, as I told you, is an optimal classifier. Because it can be seen as an ensemble of hypotheses, models in the hypothesis space, and no other ensemble of hypotheses can outperform it. For more information for a theoretical proof, see chapter 6 in this book. However, I think you don't need to that. It's intuitively obvious that it's the best because it's argmax of the posterior. So in simple words, it is optimal because it is optimizing the posterior. In the literature, it is referred to as Bayes optimal classifier. That's the reason. This is optimal classifier. Again, if you know the posteriors. Right. In conclusion, the Bayes classifier is optimal. Therefore, if the likelihood of the classes are Gaussian, now, as a result, if likelihood of the classes are Gaussian, QDA is optimal. If the likelihoods of the classes are Gaussian and they have the same covariance matrices, LDA is optimal. Now, do you see that why LDA and QDA work very well and people use them a lot? That's the reason. Okay. Any questions so far? No? Yeah. Naive Bayes classifier. So implementing Bayes classifier is difficult in practice. Why? So we approximated by naive Bayes. Why is it difficult? Can you tell? How do we calculate the posterior? That's the difficulty. So let's make assumption, simplifying assumptions, hence the name naive Bayes. Let us be naive, right? Let us be naive and accept some assumption. Okay. If xj denotes the jth dimension or feature of x is a d-dimensional vector, xj is the jth feature of x, right? Then the equation 4 that we had, which was the argmax of the prior times the likelihood, becomes this. So my likelihood becomes a likelihood of joint likelihood of x1 to xd, all of the features given that x belongs to this class, right? So far clear? Becomes a joint distribution. This is very difficult, especially when d is large, when dimensionality is large. Joint distribution, hard, right? Because also the features are possibly correlated, so it's hard to calculate. Now consider the chain rule in probability. Do you remember chain rule in probability? Do you remember that? So let's recall it. The joint distribution, for now, forget the condition. For now, forget the condition. Joint distribution of x1 to xd can be written as p of x1 times p of x2 given x1 times p of x3 given x1 and x2 until p of xd given all of the previous ones, right? Now put back the condition, right? Put back the condition. This is chain rule in probability. So naive Bayes relaxes this probability, this chain rule, and naively assumes that the features are conditionally independent when they are conditioned on the class. So it doesn't say that the features are uncorrelated or independent. It says conditionally independent. If they are conditioned on the class, we can assume that they are independent, okay? So given this joint distribution becomes a bunch of conditional probabilities, where x1 given c is independent of x2 given c until xd given c, right? As a result, I can write it as the multiplication of xj given c, where the multiplication goes from j equals 1 to d, right? I have d features, right? Agreed? Did you understand? Okay. Now let's put back this in equation 5. I will get equation 6. Right? As you see, who said this is correct? We are naive and accepted, right? So it's naive Bayes, right? Surprisingly, naive Bayes, although it's naive, works very well, right? I think it's because it's imitating Bayes, and Bayes is very optimal, right? Bayes is very optimal. Okay, now Gaussian naive Bayes is a special case of naive Bayes. Gaussian naive Bayes, it says that univariate Gaussian distribution is assumed for the likelihood or class conditional of every feature. Do you remember I told you that I have a bunch of likelihoods, right, for the features given the class? Now assume each of them is a univariate Gaussian distribution. Why is it univariate? Because it's one feature, right? Feature is a scalar, right? This is Gaussian distribution, right? Univariate Gaussian distribution with mean mu and variance sigma squared. How can I calculate this mu and sigma? Can you tell me? How can I calculate it? We have said it several times in this course. Do you remember? We can use the estimations. These are the maximum likelihood estimations of mean and variance. So basically, I approximate the mean by average of the points in the class, right? And the variance by the sample covariance matrix, or sample variance. Here, as it is univariate, it's not covariance matrix, it's variance. We learned the scalar mean and the scalar variance in high school, you remember? So, and why do I have -1? Because it's unbiased estimation. If it is biased estimation of covariance, then I don't have -1 in the denominator of variance, right? And what are these? This is indicator function saying that whether the point belongs to this class or not. To note that these have subscript of k. So for the kth class, I have how many of these equations? 7 do I have? I have d of them, right? I have d features. Let's go back to equation 6. How many times am I using this? D times, right? X1 to X3 for every class. So for every class, I have D of them, right? In other words, how many of these do I have? D times number of classes, right? Right? So we can iterate over J and also over K. Here, I'm saying that consider it for the kth class. For the kth class, I can calculate the mean and variance for the kth class. These indicator functions mean that only consider the points in that class. Agree? By the way, the whole point belongs to the class, right? Belongs to the class. However, I'm calculating it for the jth feature. Did you get it? Did you get it? How do I know whether the point belongs to the class or not? I know it because I'm in the training phase. In the training phase, I know the labels of the points, right? Okay. Now, how do I estimate the prior of the class? Nk over n, right? Exact. So it's the cardinality of class over the whole cardinality of data, right? I can estimate. So I know mu, I know sigma squared, I know equation 7, I know the class conditional likelihood, and also I know equation 10, I know the prior, so I can use them in equation 6. And equation 6 is the test phase then. So for any x, given input x, I can estimate its class, right? And this input x can be either training data point or test data point. Note that equation 8 and 9 are using training data point, right? But also this is training data point. Training. Then using equation 8 and 9, I know the parameters of this class conditional in equation 7. It gives me some distribution, right? Right? I use it in equation 6, but this x, j, can be a test data point. Do you see the delight note here? So for calculating this distribution, it has some parameters, right? Mean, variance. I calculate the parameters of this distribution using training data. But when I use that, then xj here can be the j's feature of the test data. Okay? For estimate. Do you see that? Do you follow me? Okay. Yeah. Okay. Great. According to equations 6 and 7, 6, which is this, and 7, which was the Gaussian, right? Gaussian naive Bayes is equivalent to QDA. QDA also uses Gaussian, where the covariance matrices are diagonal. Can you tell me why? Gaussian naive Bayes is using Gaussian distribution for the likelihood. QDA is also using Gaussian distribution for the likelihood. However, QDA doesn't say that the covariance matrix, it uses a multivariate Gaussian distribution. Gaussian naive Bayes is using a univariate Gaussian distribution for the features. So basically, it's assuming that my covariance in the Gaussian naive Bayes, I'm assuming that my covariance matrix is diagonal because I'm using D of them. Also, I'm assuming that they are uncorrelated. The features are uncorrelated. So the off-diagonal elements of the covariance matrix are 0 in Gaussian naive Bayes. But in QDA, I might have a dense covariance matrix. Okay? Therefore, we can say that QDA is more powerful than Gaussian naive Bayes. Note that Bayes is more powerful than QDA, but QDA is more powerful than Gaussian naive Bayes, right? It is obvious that Gaussian naive Bayes and QDA are equivalent for one-dimensional data, right? Comparing to LDA now, Gaussian naive Bayes is equivalent to LDA if the covariance matrices are diagonal and also they are equal to each other, right? So the features are uncorrelated, their variance is also the same. Then Gaussian naive Bayes becomes equivalent to LDA. Therefore, LDA and QDA, Gaussian naive Bayes have their own assumptions, so we can't say which one is better, right? One on the off diagonal of covariance matrices, and the other on the equality of covariance matrices. Each of them has its own assumption. As Gaussian naive Bayes has some level of optimality, it becomes clear why LDA and QDA are very effective, right? Any question? No. Acknowledgement. Some slides of this slide deck are based on our tutorial paper, Linear and Quadratic Discriminant Analysis Tutorial. There are more things about LDA, about QDA, about naive Bayes. I have talked, which I didn't go over those, such as comparison of LDA with t-test. So feel free to read this tutorial paper if you would like. And these are the references. By the way, the Murphy's book is also good, Machine Learning, a Probabilistic Perspective. Okay. Why am I citing central limit theorem? I think someone asked me last session that why is Gaussian distribution is important? We say it's the most common distribution in the world, because according to central limit theorem, give me a bunch of data points from different distributions, right? From different, I add them up. Approximately, the joint distribution becomes Gaussian when I add them up. Okay, interesting. The more data points there are, the more accurate this statement is. Okay, the more data points, when the number of data points goes to infinity, it becomes very similar to the Gaussian distribution. That's the reason. And we have a lot of additions in this world, right? When I'm looking at this table, I'm seeing several different lights. And they're being added coming to my eye, right? In physics, we have a lot of additions, right? Okay, the next topic, let's have a break maybe. Let's have a break and come back at 8, close to 8:25. 8:23 maybe. Okay, thank you. By the way, next topic is logistic regression, and then tree and random forest. Hopefully we can start boosting today too, hopefully. Okay, so now we cover logistic regression. If you have had deep learning with me, this slide deck might be a bit repetitive for you, but it will be short. Don't worry about it. So, logistic regression is popular in biostatistics and bioinformatics, especially years ago. Papers which were published in these areas used logistic regression a lot. And by the way, logistic regression, its name might be misleading. It's not for regression, it's for classification. And the reason that we call it logistic regression is that you can see classification as a special case of regression, where, for example, you have regress labels, and then using a threshold, you can find out which class it is. Recall preliminaries, we talked about it. So it's used for classification. Let X be d-dimensional data and Y be scalar class label. Bayes rule is this, right? Again, Bayes rule. Where Py given X is called posterior, and Px given Y is a label, is a likelihood. And Px and Py are the priors, right? In contrast to LDA, linear discriminant analysis, logistic regression works on the posterior directly rather than working on likelihood and prior. Do you remember LDA or QDA used, and also Bayes, they used this likelihood times the prior. Logistic regression directly works on the posterior, right? Okay. So logistic regression is a binary classifier. So for binary classification, where it assigns probability between 0 and 1 for belonging to one of the classes. Hence, the probability of the other class is 1 minus that probability, right? And the logistic function is used in logistic regression. Hence, the name logistic regression, because we are using logistic function. And what is that? It was initially proposed in 1845. It's so old, as you see, for modeling the population growth. Let me tell you why. This is logistic function between 0 and 1. Okay. So what are they doing? It gradually starts from 0 and then comes like this. It was used initially for modeling population growth. I think it makes sense. Why? Because initially the population is small. Then people mate, so they will have children, and the population starts to grow exponentially, right? But after a while, we have too many people, and we will have lack of food and also lack of hygiene. Because of these, some people die, right? And the population stagnates. That's the reason that it can model population. It was further, the logistic function was further improved in 20th century. You can see reference 3 for the history of logistic regression, right? So it considers the classification problem as a regression problem, where it regresses or predicts the probability of belonging to a class, right? Because probability is a continuous number between 0 and 1, so we can model it by regression. So now put yourself in the shoes of the designer of the logistic regression. I want to have the regression for predicting the probability. The simplest regression is what? Linear regression, right? Linear regression. So let's use beta transpose x plus beta 0 for regression. X is the data and betas are the parameters to learn, right? And again, we can absorb beta 0 inside beta if we consider x to be d plus 1 dimensional, an additional dimension for the sake of bias, right? We can do that. Did you understand? Okay. So beta can be d plus 1 dimensional learnable parameters for logistic model. But there is a so I can have beta transpose x, right? But there is a problem for beta transpose x plus beta 0 or beta transpose x here. Is that what is the problem? The problem is that it can predict values between minus infinity to infinity, but I want the predictions to be between 0 and 1 because it needs to be probability of it. So I need to somehow bound it. How do I bound it? I can use logistic function. Why? Because this logistic function shown here maps minus infinity to the range between 0 and 1, right? As a result, I put beta transpose x inside logistic function. So this is logistic function, also called sigmoid function. As you see, it's 1 over 1 plus e to the power minus 6, right? Now, do you agree that rather than x, I can put anything, such as Benjamin, right? 1 over 1 plus e to the power minus Benjamin. Now, rather Benjamin, put minus beta transpose x. So rather than, instead of the Benjamin or x, put minus beta transpose x. Therefore, you will get this, right? 1 over 1 plus e to the power of beta transpose x. And let's analyze this, the plot of this function. So limit this where x goes to minus infinity. What happens? E to the power of minus infinity becomes 0, right? So we'll have, it goes to 1. Agree? Limit this where x goes to infinity. E to the power of infinity becomes infinite. 1 over infinite becomes 0. Right? So it's like this. I use also 1 minus this, 1, if I have 1 minus this, I will get this, as I am denoting it here. So this is the function. 1 minus that becomes this. So 1 minus this also becomes this. What is this? Let's analyze its plot. E to the power of beta transpose x over 1 plus e to the power of beta transpose x. Limit this where x goes to infinity. What happens? It becomes infinite over infinite. It becomes undetermined. You need to use L'Hopital. I don't know if you have heard of that. L'Hopital rule. We used to learn it in high school. I don't know whether you learned it in college or high school or university. So limit this. It goes. You will see that the limit becomes 1. Now limit this where x goes to minus infinity. Becomes 0 over 1 plus 0. Becomes 0. Right? Right? Okay. So I'm using these two as the probabilities of the classes. They sum to 1, right? They sum to 1. So I can use, and also each of them is between 0 and 1. I can use them as probability. So let me assume that probability of class 1 is this and class 0 is this, right? You can use the other way around, doesn't matter. But whatever you use for this, you should use it for test phase 2. So if I'm using this for class 1, even in the test phase, I should use that for class 1. Okay. This logistic regression can be seen as a neural network with one neuron, where the activation function is a nonlinear sigmoid or logistic function. Why? So what do I have here? This part is just linear regression. That it is modeling beta transpose x, right? Or beta transpose x plus beta 0, right? You can see it as similar to the summation that we have in neural network before activation function. Because every layer of neural network before activation function is a linear model, it's a linear projection, okay? And then we feed it to the logistic function, and the whole thing becomes logistic regression. As you see, it's a one neural network with one neuron, whose activation function is logistic function. Now let's see how we can train logistic regression. Consider n data points, x1 to xn, and their labels y1 to yn, right? So in the data set, assume that they are independent and identically distributed. In short, IID. So they are independent and their distributions are the same. Then the posterior becomes over all of the data. What does it? So posterior was probability of y given x, right? Right? So you can write it as why can I say multiplication? It's kind of a joint distribution and they are independent. So I can write multiplication. And for every point, I can have the point is either in the class 1 or class 0 in the training phase. I know the labels, right? So I can write it as either probability of class 1 if it belongs to the class 1, or plus probability of class 0 if it belongs to the class 0. This I is indicator function, right? So for every point, either I have the first term or the second term. It's either 0 is the probability of class 1 plus 0, or probability or 0 plus probability of class 0, right? Did you see that? Okay. Now I have multiplication, and inside the multiplication I have a plus. This is a pain in the neck, right? This is a pain in the neck. How can we get rid of this plus? We can use a technique, which is a nice technique in machine learning. I can say, let me not use the indicator function, but put yi, the label, as a power. Yi and 1 minus yi as a power, where my yi is either 0 or 1. Okay? So if it is 0, this term becomes 1. Right? And I will have the second term. If it is 1, this second term becomes 1, and I will have only the first term. Agreed? Now, as a result, my posterior becomes this. Why? If you substitute the logistic functions of equation 2 and 3 in my posterior in equation 5, I will get equation 6. So far clear? Okay. Now I have this. There are two things which are pains in the neck here. Multiplication, also exponential operator. Okay. For getting rid of these, I can use, what is the opposite operator of exponential operator? Logarithm, natural logarithm. So let's use the log posterior. This is the reason we usually use in machine learning, we use log likelihood or log posterior, right? This is the reason. If we do that, we know that logarithm of multiplication becomes summation of logarithms. So this multiplication becomes summation, logarithm goes inside. Also, so I will have logarithm of this term, also logarithm of this term, right? This power comes behind the logarithm according to the properties, right? Also, I know that logarithm of a over b is logarithm of a minus logarithm of b. So I can simplify the fraction in logarithm, right? I will get this. And so now I multiply this to the sides, to the elements. So let me see what I'm doing here. Here, this exponential operator and logarithm cancel each other. I will get this. Also, this is the second term. Multiply these two terms to this term. I will get these two terms, right? Agree. Now, interestingly, these two cancel each other, right? I will get this. So far clear? So this is my log posterior. I'm repeating that, what we found. Now, we need to do what? This is log posterior. Should I minimize or maximize it? Should I, what? Why minimize is posterior? Posterior is the probability. Should I minimize the posterior, the probabilities of the classes? No. So this is, I know the probability of the classes happening in the, so the probability of that, my data, whose label is 1, belongs to class 1. Also, the probability of my data, whose label is 0, belongs to class 0. This is the posterior. Should I minimize it or maximize? I should maximize it, right? So I should, now that I think you also have heard of that maximum likelihood estimation. Why do we say that? You are maximizing the likelihood. Here we are maximizing the posterior, right? So we need to maximize that. Maximization of this is our cost or fitness, whatever. Maximizing this, right? It's an unconstrained optimization problem. What should I do? What did we learn for maximizing a function in high school? Yeah, we should take derivative, set it to 0. If we can find a closed form solution, done. Otherwise, we need to do it iteratively using numerical analysis, right? Then we can use first order optimization or second order optimization. Here, if you take derivative, set it to 0, you will not find a closed form solution. We need to do it iteratively. Let's do it using second order optimization. We usually use second order optimization, or also called Newton's method, right? So let's use Newton's method for finding beta. And we know that optimization variable is beta, which is d plus 1 dimensional, right? So we need both first order derivative and second order derivative. Let's first calculate the first order derivative. Derivative of this log posterior with respect to beta. Log posterior is a scalar, beta is a vector. As a result, derivative is a vector. Recall preliminaries. So what is this? Beta transpose xi. Its derivative with respect to beta becomes xi, right? Why do I have summation and summation doesn't go away? Because I'm taking derivative with respect to beta and I have xi. So I have the summation. If I were taking derivative with respect to xi, the summation would go away. Okay. And Also here, I need to do chain rule. So derivative of logarithm, and then I go inside the logarithm. I have derivative of 1 is 0, and derivative of e to the power of beta transpose xi. Again, I need to do chain rule. Derivative of exponential operator, and then derivative of beta transpose xi. Right? I will have nested chain rules. So I'll get this. And as expected, it's a vector, as expected, because this is a scalar, this is a scalar, this is a vector, because I know this derivative must be a vector, right? So I can factor out xi. Interestingly, I have xi at the right-hand side of both terms. Factor out xi. Also, the transpose of this first order derivative, it transposes this vector, right? Now, my second order derivative, I can write it as the first order derivative of first order derivative, right? I can do that. But I need beta transpose. So I need first order derivative of transpose of first order derivative, because my Hessian needs to become a matrix, okay? So I have this first transpose of first order derivative. Now let's take derivative again. This, we know that derivative is a linear operator. It goes over the summation. The summation is here. I will have this. I know xi transpose is a constant with respect to beta, comes out of the derivative. Now I define this. I define it, right? You can define it to be Benjamin. I define it to be probability of xi given beta, right? As a result, I replace this with probability of xi given beta. Okay. Now so as you see, I have this term inside. Let's simplify it. Let's calculate this. It's here, right? So what was that? This derivative of this with respect to beta. It's a fraction. I use the formula for derivative of fraction. We learned all of this in high school. Everything goes back to high school. Okay, so we see this, and it basically I'm using the derivative of numerator and also the derivative of denominator in the formula, and using chain rule, etc. Then what happens? Let me see. Let me think. Okay, interestingly, I have e to the power of beta transpose xi, a scalar. In both cases, I factor it out. Okay. Also, interestingly, I have xi on the right-hand side, because this is a scalar. Doesn't matter, right? Xi in both, so I factor it out, and I will have this. Interestingly, these two cancel each other. I will get this. I can rewrite it as a multiplication of these three terms, right? Interestingly, the first term is probability of xi given beta. The second term is 1 minus probability of xi given beta. And the last term is xi, right? As a result, this derivative became multiplication of these three things. I put them back in equation 9. I will get equation 10. Let's see if we did it correctly or not. The Hessian must be d by d. D plus 1 by d plus 1, right? This is d plus 1 by 1. This is 1 by d plus 1. So this is d plus 1 by d plus 1. Correct, right? Recall that we put one additional dimension in x for the sake of bias. Okay, so now we could calculate a Hessian. We can do the Newton's method for maximization, but let's make it matrix form, because we don't want to use for loop in our code and these things. Let's do it in matrix form. So I define matrix X to have d plus 1 rows and n columns. What does it mean? I'm stacking the data points column wise, okay, where I put 1 at the start. Then I'll define the matrix Wn by n as a diagonal matrix whose ith diagonal element is this. Also, I define the vector y, which is the vector of labels. Also, the vector p, which is n-dimensional vector whose elements are these. these logistic functions, right? Now compare these. So see the first order derivative. This is first order derivative. Can you take a mental picture from that? Y minus something, the logistic times xi. In matrix form, it becomes y minus p, the logistic, times x, right? But because of the in matrix multiplication, the dimensionalities should match, so x becomes behind the term y minus p. Also, I have the Hessian. If you compare this element-wise Hessian with the, so I have p 1 minus p x transpose as a result, so it's quadratic with respect to x. So I'll have x transpose. In the middle I have w, which has these elements, right? Minus, right? Agree? So as a result, my Hessian is this, my first order derivative is this. I can use Newton's method. What was Newton's method? It's this, right? The previous beta plus Hessian inverse gradient. Why am I using plus? Usually in Newton's method it's minus, because it's Newton's method for maximization, not minimization, right? But why do I have minus here? It's not because of Newton's method. It's because of the Hessian. Hessian has minus. Okay? And tau here is the iteration index. Repeat it until convergence of beta. You see that? In the test phase now, training phase is over. We found beta, right? In the test phase, now for a point x, which can be training point or test point, we feed it to the logistic function. If it is greater than half, it means that probably it belongs to that class. If it is less than half, it belongs to the other class. But which class? What is this logistic? We used it for which class? E to the beta 1 over 1 plus e to the beta. We should go back, and we saw that we use this for class 1. So if this is greater than half, its estimated class is 1. Otherwise, it's class 0. Agree? Interesting. Comparison to LDA. Let's compare it to LDA. Logistic regression estimates d plus 1 parameters in beta. Do you agree? Okay. But LDA estimates many more parameters, right? Let's see why. Let's see. By the way, I asked you, do you agree? You said you nodded yes, but can you tell me why? Why do I have d plus 1 parameters in beta in logistic regression? My beta was d plus 1 dimensional, right? What were I finding? Beta. So I have d plus 1 unknowns, which I find. Okay. Now in LDA, let's see how many parameters we are having to learn. Recall LDA, which we talked about in previous sessions. So we had prior of each class, and each prior is a scalar. And I have 2 classes in LDA, so I have 2 times 1, 2. Also, I have mean of each class. Each class has a mean, a d-dimensional vector, right? So we have 2 classes, so 2D. Also, we have covariance matrix of each class. It's d times d plus 1 over 2 parameters. Why? Because covariance matrix is symmetric, right? So only half of the matrix, the lower triangular or upper triangular matrix, is enough, right? The elements. And we have 2 classes. So in other words, I have d times d plus 1 parameters for covariance matrices. If you sum them up, it becomes d squared plus 2d plus 2 parameters to learn. Compare it with d plus 1 parameters that we need to learn in logistic regression. Logistic regression has much less number of parameters to learn, right? And we know that, what does Occam's razor say? The simpler explanation, the better, right? Also, LDA assumes the distribution of each class is Gaussian. Do you remember? With the same covariance matrices, right? Here we didn't make. Did we make any assumption on the distribution of classes? Okay. Interesting. In logistic regression, we don't make such assumption. By the way, you might be wondering, we use logistic function. We use logistic function for modeling probability, not the distribution of the classes. Okay. Acknowledgement: some slides of this slide deck were inspired by teachings of Professor Ali Qudsi at the University of Waterloo Department of Statistics. And these are the references. Any question? No? The next topic is tree and random forest. Okay. First, let's talk about tree. Tree is used for classification or regression, right? Okay. It is easy to implement, so its benefit is that it's easy to implement. In coding, we need recursive functions for modeling tree, right? Because why? Why is it recursive? Because exactly for the same reason that how do we reproduce? How do humans reproduce? Two people mate, they have a child. That child later becomes a parent again. So we have every child is the parent of the next generation, right? Something like that. So here again, we have a tree. We have a parent node, has children. Those children nodes also become the parent node of several other children. So that's the reason tree is recursive. Okay. And also it is intuitive, because one of the problems of some complicated machine learning algorithms is that they are not explainable very well. It's explainable, right? It's easy to understand. It's intuitive, and how it works is explainable. It is common to use in biostatistics and health sciences. Okay. And now assume we have a data set of x1 to xn and their labels, y1 to yn. By the way, the labels can be either continuous for regression or discrete for classification. xi is d-dimensional vector and yi is a scalar label. And let xi be this, where xij, let it denote the jth dimension or feature of xi, okay? A tree partitions the space into regions, okay? Let's see an example here. Consider the two-dimensional space like this. So xi1 and xi2, right? Feature 1, feature 2. So consider xi1. We say it's with whether it's less than some threshold S1 or not, greater than S1. If it is less than S1, come here. If it is greater than S1, come here, right? So as you see, xy1, I have S1. This is the threshold, right? This is the threshold. Here, go to left or go to right. So I'm partitioning the space, right? Now let's go to left, for example, which is here, meaning that xi is less than S1. Then again, I have a sub-region. I can partition this sub-region into sub-regions as well. So how? Now I can say whether xi2 is less than or equal to S2 or not. If yes, come here, otherwise go here, there. So xi2, S2, either I'm less than S2, I'm come here, I'm region 1, or I'm greater than S2, I'm here, region 2, right? Now let's traverse the tree in the other way around. Here, I'm xi1 is greater than S1. Now xi1, again, I can have the condition of x on xi1 again here. Is it less than or equal to S3 or not? If yes, I'm here in this region. Otherwise, I'm here. Go left. So when I'm here at this point in the tree, I'm somewhere between here, because I need to be also greater than S1 because I already traversed here, right? So now again, I can say, for example, whether xi2 is less than S4 or greater than S4. If less than S4, I'm in region 4. Otherwise, I'm in region 5. If xi1 was greater than S3, I'm in region 3. Okay? So I'm partitioning this space. This is 2D. You can have any number of dimensions. If it is 3D, it's like a cube, right? You partition this cube. But here, by the way, we had binary tree, where every node, every region is partitioned into 2 subregions. We can have general tree, where every region partitions into 3 regions, subregions, or 4, whatever, right? The initial region is the whole space, A binary tree, so every node has 2 children. It splits a region into 2 disjointed subregions, So the union of the 2 subregions becomes the parent region, and they don't have any overlap. Okay. Whose union is a parent region. So basically region 1, JS. S is a threshold. J means the jth dimension, right? Is when all of the xi's, where xij is less than or equal to S. Region 2 is all of the xi's where xij is greater than S. The whole region R is the union of R1 and R2, but their intersection is empty. J goes from 1 to D. S is threshold of a split, right? Now there are some questions. Over which feature J do we split? Over which feature? That's one question. Another question, what is the value of the threshold S? Right? What is the value? Which threshold do I use? The third question, what constant value estimated label should I assign to every region? Because I want to assign some label, some estimated label to every subregion for the sake of regression or classification. What value do I assign to that region? Okay, so 3 questions arise. Now let's answer them one by one. Okay. So we define some cost function named, recall that everything in machine learning is optimization, right? So we need to have some cost function. We call it local cost function of the tree, local cost function of the tree as equation 5. What does it say? So I have minimize these 2 terms subject to J and S. J is the integer index of the feature. S is some float threshold, right? That integer index makes this hard to optimize, right? Because it becomes a discrete optimization problem. Whenever in optimization you hear discrete optimization, you need to be scared. Okay, you need to be scared. It's hard. So we will see what do we do. R1 and R2 are the 2 subregions that the parent region is 2. Okay. J is the feature to split over as one of the optimization variables. S is the value of the threshold as the other one, the other optimization variable. What are C1 bar and C2 bar? They are the mean labels of the subregions, because I have some training data points, each of which are in some region of the space, right? When I partition the space using the tree, in every subregion, I have some data points, and they have some labels. Let's take the mean labels of the data points in that region 1, denoted by C1 bar. the mean labels of the data points in the region 2 denoted by C2 bar. As I said here, average of yi where xi belongs to R1, average of yi where xi belongs to R2. Therefore, we find the best j and s so that, so now let's analyze this cost function. Can you tell me what is this doing? Can you tell me? Yi, by the way, is what? Is my predicted label, right? So basically it says that I want the smallest mean squared error of the estimation of the labels in the regions. Okay, so yi is not the predicted, I apologize, is the actual label. So basically it says that equation 5 says that find j, the splitting feature, and the threshold s in a way that this is minimized and this is also minimized. What are these two terms? How much my actual labels of the points in this region are away from the average label of that region. One. Also, the second term says that how much my actual labels of the points in the second region are away from the mean actual labels in that region. Basically, it means that how different the labels in that region are. If the label in a region, if the labels are too different, yi minus c1 bar becomes large. Do you agree? Because the mean will be some middle value, but I have outliers. This mean squared error is large. Simple example. Assume one region has 1, 1, 1, 2, 1. The mean becomes what? For that region, 1 plus 1 plus 1 plus 2 plus 1. So 4 plus 2, 6 over 1, 2, 3, 4, 5, 6 over 5. Right? Then what is mean squared error? 1 minus 6 over 5 squared plus 1 minus until all this mean squared error for all of them, sum them up, right? Now consider another case. 1, 2, 1, 2, 1. Okay. Assume I have 3 classes, maybe 1, 3, 2, 1, something like that. They are very different. So C bar becomes some middle value, but I have a lot of difference from 3 and the mean 1 and the mean. So the mean squared error here goes up, right? And I think it makes sense now to you. Why am I minimizing this? Because I want to find the feature and the threshold in a way that my partitions become very pure in terms of labels. Okay, if a region has pure labels in it, the mean squared errors of that region becomes 0, right? What do I mean by pure? I mean the labels of all of the points in that region are equal to each other. Okay. So this optimization problem makes sense. Now, if the depth of the tree, by the way, I think I will tell you how to solve this. If I haven't, but anyway, can you tell me? We'll talk about it. That how to solve this optimization problem. I told you that it is going to be hard because J is discrete. We will talk about it. But before that, let me analyze overfitting and underfitting in tree. If the depth of the tree is small, what do I mean? I don't grow the tree very much, right? Then the number of children regions is small. Do you agree that the more depth you have, the more children you will have? Just visualize the tree in your mind. If I have a small depth, I have some number of trees, grow the tree, and you will have too many children, right? So for the small depth, the number of children is small, so it is underfitting. Why? Because I didn't partition the space enough. And my partitions of the space have impure labels a lot of different labels, right? Now, what if I grow the tree too much? I will have too many children. What does it mean? I have too many small partitions in my space. this becomes overfitting. What is the worst case scenario for overfitting? That every region has only one single data point, right? One single training data point. Therefore, the number of children nodes, okay, the number of children in a tree, T is denoting the tree, is a good measure of overfitting. Do you agree? The more children I have, the more overfitting I have. And also, we know that overfitting can be modeled as complexity, right? It is showing the complexity. We talked about it before. So it's a good measure of overfitting and complexity. Let the number of children be denoted by cardinality of T, okay? Question, how large should a tree be? In other words, how many children should I have, okay? So solution 1, keep splitting the tree until the validation error starts going up while the training error is going down. So I can have training data, test data, validation data, right? Whenever for whatever tree, I can grow the tree. At every depth of the tree, I can calculate the validation error. And initially, the validation error is large. It decreases because I'm having more partitions. But after a while, what happens? The validation error goes up. Do you know why? Because I only made partitions according to the training data. The training error goes down. The do you remember this mean squared error? The mean squared error of the labels for training goes down because I'm finding the J and S based on the training data. But I'm not finding them based on the validation data. When the validation data error goes up, starts going up, it means that I'm starting to overfit. Recall the regularization lecture that we had several sessions ago, right? Then we can stop. Why am I not using test error? Because that will be cheating, right? Cheating, we talked about it. Why am I not using train error? Because it's bad for me. I will not find out overfitting. I should use validation. Okay? Recall regularization lecture that we had. Solution 2, another way that we can do that, is that consider the global error of the tree. That was the local error that we talked about, now global error. Global error is defined as this, summation of NM QMT. M is the index over the children. In other words, the index of the subregions, partitions of this space. Do you see that? So summation is over the children nodes. NM, so what is this? Indicator function of xi is belonging to the region Rm. NM is the number of points in the partition M, right? Did you understand? Partition M, Rm is one of the partitions. It has some data points in it. NM is the number of points in there. And QM, so we talked about it. QM, what is QM? QM is the average error of the child region Rm. Do you remember? I told you we have mean squared error of every region has some mean squared error of the labels from the mean label in that region, right? Do you remember that? Now use that mean squared error divided by NM because I want it to be mean, average, right? This gives me QM. Do I want QM to be small or large? Small. I want it to be that. So I say summation of NM QM. Basically, that's the summation of mean squared errors of the regions, but I scale them by NM. Okay? To be fair between the partitions. I want it to be minimized, right? I call it global error. We can calculate the global error of the tree after every split. And if there is not a sufficient decrease in the global error, we can stop. You see that? Because it goes down, right? It's a training error, by the way. At some point, we don't need to partition further. It's not decreasing too much. Then we can stop. Agree? However, this solution is not good, because what I'll tell you with this example, I'll tell you why. This solution that I just told you is not good. Because what if the global error in the next split suddenly decreases drastically? Look, how do you know that? Because it's decreasing. What if in the next step it decreases drastically? Can you see the future? According to the causality, we can't see the future, right? What if the next step, maybe if you had split one more time, the error would go down drastically. An example is this. Consider this 2-dimensional space. I partition it once. It's not decreasing the error much. But if I stop there, I will harm myself. Why? The next split would decrease the error very well, right? That's the reason, because we can't see the future. This is like a chess game where we should consider the long-term reward or cost and not only the short-term reward or cost. That's also related to reinforcement learning. We need to see further. In chess, you might sacrifice your queen, right? But you know that in 10 moves, you will win, right? You need to see the future. Solution 3. Another solution is using regularization. Okay. So we grow the tree by the local error optimization for every split. Do you remember we talked about it? As done in equation 5. We minimize this. We grow it, right? And then we prune it back. We prune it. Prune it by the regularized cost global error. This was the global error, do you remember? Now I regularize it by the number of children. Because this is bad, I want this global error to be decreased. Also, I don't want to have too many children, because too many children means overfitting, right? So also have alpha is the regularization parameter greater than 0, right? We talked about QM before. This is regularized global error and this is local error. Pruning, what is pruning? Is the opposite of splitting regions. So exactly like we are gardening. When you are gardening, what do? You prune the trees, right? The leaves, right? You prune it back. Opposite of splitting. It is collapsing or merging child regions into the parent region. So the parent region becomes a new child region. Okay. For pruning, we merge the child tree, merge its children, which has the smallest regularized global error. So how do we do pruning? We have a bunch of children, right? Which two children do we merge? The one which minimizes this the most. Sorry, which minimizes this the smallest. Do you know why the smallest? Do you agree that if I merge two children to become one parent again, I'm increasing the error? By pruning, I will definitely, because by splitting, I decrease the training error. By pruning, I increase the training error. Now I want to have the smallest increase of error. Did you get it? Did you get it? No? So, do you agree? This is my tree. Assume this is my tree. Okay? Do you agree if I merge these two to become one parent, this increases the training error? Why? Because previously it was like this, right? Then I split this region into two children, right? When I do this during this process, I decrease the training error, right? So the opposite should increase the training error. Pruning increases the training error. But the problem is that I can merge these two. I can also merge these two. Which one do I merge? Which one do I prune? I don't want to increase the error too much. Prune the ones which increase the error the smallest. So I prune them to the two children which minimizes this global error. Did you get it? This is because the child tree plays the smallest role in decrease of the regularized cost of the tree. I want to have the smallest increase of the error. Now question. Why do we grow the tree until the end and then prune? We talked about it, right? For the same reason as the chest, as I said. How do you know you are splitting? How do you know that you should stop? Maybe if you split further, drastically the training error goes down. So the philosophy behind pruning is that go until the end, go to complete overfitting to see the future, and then prune back. Right? I wish we could do it in our own lives too. If we could experience everything, then come back and relive. Right? That's the reason. This example says that future splits might be better. Now, algorithm of regression tree in summary. Grow the tree iteratively, recursively until some long enough depth using this. I didn't tell you how to do the optimization. Now I tell you. I want to find J and S, right? J is discrete, S is float, right? If it was S, maybe it would be easier. J is discrete, it's a pain in the neck. But interestingly or happily, J, the options for J is finite. J is 1, 2 until D, right? So I can simply use for loop. Use a for loop over the possible values of J, right? And maybe use several values for S and do a grid search. Okay? Do a grid search. Basically means that calculate this cost for different values of J and S and see which combination of J and S minimize this system. Right? So you can do that. And you can change S with fine steps. The finer, the better, right? Of course, it's a trade-off between accuracy and speed. And so grow the tree until some long enough depth using this. So this at every split tells you which feature to split on and which threshold. Then prune the tree iteratively until depth becomes the desired depth. Okay? Using this global. So basically, we are growing the tree using local cost. We are pruning the tree using global cost. Okay? Now we can use tree for classification, right? Usually it's called decision tree because we decide based on it. Sometimes they use decision tree for regression too, doesn't matter. Okay. The tree can be used for classification. It's called decision tree because it decides the class label of the data points in the regions. The cost of the decision tree should be a loss for misclassification. Can I use mean-squared error this time? I can, but it's better to use the losses for classification. Why can I use mean-squared error for classification too? Because classification, you can see it as a special case of regression, right? But let's use actual loss functions for classification. So assume there are C classes and L denotes the label of the Lth class, okay? Then I can define PML as this. 1 over NM. NM is the number of points in the region Rm. I is the indicator function here, which is 1 if it satisfies its condition, otherwise it's 0, right? So basically it says that, what is this? Can you tell me? It says, let me think. Oh, PML, it has two subscripts, M and L. M is for the region, L is for the label, right? So PML basically means the probability of the class L in the region M. How do I calculate this probability? I have total number of points in the region. I have number of points in the class L in this region. I divide the number of points of class L in this region over the total number of points in this region. This becomes some number between 0 and 1. I consider it as a probability. And if I do it for all of the classes in this region, the summation of these become 1. These probabilities becomes 1. Right? In other words, numerator is the number of points of class L in the region M. The denominator is the number of points in the region M. Now, can you tell me, the PML so shows what fraction of points in the region Rm have class label L? In other words, how pure the region is for the class label L. If PML is close to 1, what does it mean? Most of the points in this region M have class label L, right? If it is close to 0, it means that I have too few points of class L in this region, right? So this is what we had. I'm repeating it. Now we can have various cost functions, such as these: misclassification error, Gini index, cross entropy. So misclassification error is equation 13. What does it say? These are errors, right? I want to minimize them. So 1 minus PML, I know, do you remember PML should be large, right? To be pure. If PML is close to 1, it means that that region is pure for the label L. So I want to maximize PML. As a result, I want to minimize 1 minus PML, right? Right? I want to increase. Why do you ask me if you didn't follow? Did you get it? I want to increase PML, so I need to decrease 1 minus PML. And I do it over all of the regions. So this is the cost of misclassification error. Another one is called Gini index, defined as this: PML times PMK. Then I have summation over the regions. Also, I have summation over the class labels, where L goes from 1 to C, but L is not equal to K. What is it saying? It has an interesting insight. When PML increases for some class, it decreases for some other class, right? So increasing PML for one of the classes is good, but at the same time, it decreases PML for the other class, which is bad. So there is a trade-off. Oh, do you see that? So if PML is close to 1 for one of the classes, that's good for me. The other one, it gets very small. The multiplication of these two will become what? Can you tell me? So consider PML large. This is desired for class L, right? Because doesn't matter which class label it is, it's desired because it purifies that region. But when PML increases, PMK decreases, and PMK becomes close to 0. As a result, their multiplication becomes small, as desired, because I'm minimizing this. I want the multiplication to be small. When does this multiplication become small? Either PML is small or PMK is small. Both are desired, because when PML is small, PMK is large. When PMK is small, PML is large. Both are desired. Did you understand the philosophy behind Gini index? Yes? What? Why? So it's considered two classes. Okay. So PML plus PMK becomes 1. Because L goes from 1 to 2, L is not equal to K. So I have two probabilities of the classes P and 1 minus P, right? So it will be P, the other one will be 1 minus P. Do you agree that if P is 0.9 is good, if P is 0.1 is also good? Both of them means that P equals 9.9 means that the region is almost class 1. P equals 0.1 means the region is almost class 2. Both are good. I want the region to be pure. I don't care which class label it is. Now generalize it to several classes. Okay. And as I'm considering the summation over all classes, I'm considering all of the permutations. The cross entropy now, it's this. PML, log of PML, I have summation of the classes, summation over the regions, and minus. Okay. So if I don't, basically, when you minimize the cross entropy, it separates the classes better. It's related to information theory as well. We will see their plots. We'll see their plots. By the way, I think it also makes sense. Its philosophy is similar to Gini index with some slight difference. It has logarithm. But there is another difference too. In Gini index, I have summation of the pairs, so I have double summation. In cross entropy, I have one summation. But the philosophy behind that is similar. But note that this is one summation. This is two summations. We will see the figure, I think, is very obvious here. So consider these three errors. This is a very famous plot for the misclassification errors in decision tree. So this one is misclassification, this triangle one. I'm plotting this. So because PML is between 0 and 1, right? So you can have the plot of error with respect to PML. And by the way, cross entropy is not between this region. So we are scaling it to pass through the point half and half. Okay, we are scaling that. And if you do that, this is misclassification error. This is Gini index, and this is entropy. Does this plot make sense? What is it saying? Let's analyze this plot. What is it saying? We want to minimize the error, right? We want to. So the error should be around here, right? Where do I have this? Either here or here. Again, that's philosophy that I told you. If PML is close to 1, that's good because it's pure. The region is pure. If PML is close to 0, that's also good because the other P will be close to 1. That region is pure, right? Did you say? But in the middle, it's so confusing. Consider the two classes. It's half-half. Completely so confused. The region is confused with between the classes, right? Now noise injection to data in trees. By the way, this, as you see, this is the plot P times 1 minus P is an important function. You see that a lot in probability in the papers about probability. Okay, sometimes you want to maximize this P times 1 minus P, and I think you just saw that the maximization is half, for example, right? Minimization is either P is 0 or 1. Now noise injection to data in trees. One regularization technique So we are talking about regularization techniques now in 3. Okay. One regularization technique in trees is noise injection to input training data at some level. Noise injection to data is a very common technique in regularization. Recall the lecture of overfitting. Do you remember? We talked about this, right? When instance is not in the training set, the error that we have is a good estimation of the actual error, the true error. When the instance is in the training set, I have the complexity term as well, right? And this is the actual error, and this is empirical error. Now, if we do not add noise to data, let's talk about these sigmas now. So what was sigma? Recall that lecture. Sigma was the variance of noise. Sigma squared was the variance of noise. So if we do not add noise to data, sigma is 0. So we get this. Consider this. The complexity term goes away. This also goes away. Doesn't matter. Okay. For training data. So basically, my complexity term has sigma squared in it. Do you see that? It's multiplied by sigma squared. If we do not add noise. And we will not understand when it starts to overfit. Therefore, if we get overfit without knowing, it will work poorly in the test phase. Let me rephrase it better. Assume I have my training data and I train it. For example, using any machine learning algorithm such as trees. I don't inject noise to it, okay? I want to justify why noise injection, small noise injection to data is good. If I don't add noise to it, what happens? I will have this complexity term, right? And we will have, and the empirical training error will not be a good estimate of the actual true error, right? Because of that complexity term. But what if, sorry, not inject noise. I think I'm getting tired. Not inject noise. Sigma is 0. The actual error is this, right? We never find out that we overfitted. But when I inject noise, sigma is not 0, right? Sigma is not 0. Then I will have error, is error plus complexity. In this case, I will find out that my error goes up because of this complexity. Did you get it? Did you get it? This is the reason that we can, when we add noise to data, we find out when we get overfitted. Now let's talk about random forests. For random forest, you need to understand bagging. So bagging is nothing related to bag. Initially, when I learned that, I thought it's related to bag. No, it's short for bootstrap aggregating. Okay, it was first proposed by reference one in 1996. Okay, it's a meta algorithm. What do I mean by meta algorithm? An algorithm which uses other algorithms in it is called meta algorithm. It is a meta algorithm which can be used with any model, any classifier, regression, etc. Okay. The definition of bootstrapping is as follows. So now let's talk about bootstrapping in the statistics. Then I will talk about bagging. Suppose we have a sample x1 to xn with size n, where f of x is the unknown distribution of the sample, right? That is xi, they are IID, independent and identically distributed, with the PDF of f of x. We would like to sample from this distribution, but we do not know the f of x, okay? approximating the sampling from the distribution by randomly sampling from the available sample is named bootstrapping. Let me tell you what I mean. I have a bunch of data points, okay? These data points have some joint distribution, do you agree? I want to sample from that distribution of these data points, but I don't know that PDF. Bootstrapping says sample using these available data points. Okay, how do I do that? We use simple random sampling with replacement. It's kind of, the philosophy is a bit interesting. It says you want to sample from the distribution of these data points, but you have these data points in hand, use them, take from them. If you take from these data points, it's like you're taking sample from that distribution. Okay, but it says sample from them with replacements, because you might not have too many points. Sample with replacement. Okay, when you sample with replacement, it's called bootstrap sampling or bootstrapping. Okay, now in bagging, which is bootstrap aggregating, we draw k bootstrap samples, each with some sample size. So we take some samples, k samples with some sample size, right? Then we train the model HJ. This model can be anything, because it's a meta algorithm, can be any classifier regressor. Right? Train the model HJ using the jth bootstrap sample, where j goes from 1 to k. Okay, I have k bootstraps. Hence, we have k trained models rather than one model. Basically, what does it mean? I have some samples, take some dataset, randomly dataset, sub-sample from this dataset, big dataset, train that one model with it, right? Then do it's sampling with replacement. Take another sample, another dataset out of this huge dataset, right? Train the second model. Do this k times. We will have k models trained by k different samples. Okay. Now we aggregate them. Hence the name bootstrap aggregating. We aggregate them. How can we aggregate them? The simplest thing is what? Because every model has some prediction, right? Hj of x, where x is now can be test data point. I have already trained them. I can use them in the test phase, right? I want to aggregate. So I train k models. Now training is over. Now in the test phase, some x comes. I can feed this x to each of these k models. It gives me some predictions. So I will have k predictions, right? What should I do? If it is regression, take the mean. If it is classification, take the majority vote. What? Majority vote, right? So if it is regression, take the mean. If it is classification, either do the majority vote or take the mean and then use the sign of the prediction, the sign of the mean prediction. Because consider if it is binary classification, the sign becomes 1 or -1. Somehow use as summary statistics of the k predictions, right? This is called bagging. Now you might say, why is bagging useful? This slide explains why it is useful. Let EJ denote the error of the jth model in estimation of the observation of an instance. Okay. Suppose this error is a random variable with normal distribution having mean 0. So EJ, by the way, we have several models, right? EJ is the error of the jth model. And they are IID, Gaussian with mean 0, variance S. Okay. S is the variance of the noise of the error of the jth model. We denote the covariance of the estimations of 2 trained models using 2 different bootstrap samples by C. So Do you agree that I have several models, right? Consider two of the models, okay? Two of the models, they have covariance of the estimations, right? This has some estimation, this has some estimation. I can have covariance of the estimations, right? I denote it by C, okay? So as a result, recall preliminaries. This is EJ. Expectation of EJ squared becomes what? S. Let me tell you why. According to this formula, do you remember we had it in preliminary? What is variance of EJ? This is S, right? We just said that. This is it. What is expectation of EJ? According to this, it's 0, right? So it's S minus 0, it's S. So this is S minus 0, which is S. As a result, this expectation of EJ squared is S. Did you get it? Did you get it? What about expectation of EJ-EL? Recall this formula from preliminaries. Covariance, formula of covariance. What is expectation of EJ? It's 0. Expectation of EL is 0. What is expectation of EJ-EL? I don't know. I want to find it. What is covariance of EJ-EL? I denote it by C. Do you remember? So expectation of EJ-EL is C. Okay? Clear? Now I'm going to use these two. According to these equations, 16, 18, and 19, what was 16? It was 6. This was 16, the aggregation. What is variance of F hat? So F hat was what? The mean of the estimations, right? Recall preliminaries. I don't know if you remember. The constant becomes a squared constant because variance is quadratic, right? Therefore, I have variance of summations. Do you remember the formula of variance of summations? Recall preliminaries. We talked about it. It's this. Summation of variances plus summation of pairs of covariances. Also have 1 over k squared, 1 over k squared here, right? Then, what is this? What is variance of HJ? S. So I have summation of S plus k times, right? So I have k times S. What is covariance of HJ and HL? We just said we denoted by C, right? So I have summation of C. How many times? K times k minus 1 times. Because it's not k squared. Why? Because of this condition. L is not equal to J. Okay. K times k minus 1. C, right? Now simplify this k with this, I'll get this, okay? Now it becomes interesting. Just focus for a few minutes and it's very interesting. So this is variance of the aggregated estimation, right? Now, what if the samples, if two trained models with two different bootstrap samples, right, are very correlated, very similar to each other. What happened? C becomes almost S. Why? C was the covariance, S was the variance of one of them, right? Then I replace C with S. What is this? This becomes S. Okay? What if the two trained models are very different, uncorrelated? What happens? Then C becomes almost 0 because they are uncorrelated. So I replace C with 0. I will get 1 over k times S. S is bad for me, right? Because that was the variance of the error, right? What does it say? What these two say? They say in my bagging bootstrap aggregating, I want the models to be uncorrelated, very different from each other, because the variance of the estimation becomes 1 over k times s. But if they are very similar to each other, it becomes s. S was the, I will finish soon. S was the variance of one of them. Basically, in simple words, in bagging, if all of the models are the same, it's like using one model. You're doing nothing. The variance is still S. But if they are very different from each other, it divides the variance of estimation by k. So it reduces the variance of estimation, right? So bagging helps reducing the variance of estimation, right? So it helps us not to have too much error. So it helps to have several case models, but these models need to be different, right? Need to be different. Otherwise, it doesn't make any sense. This is called, and also called ensemble learning, also called model averaging. Okay, because we are using model app, we average we aggregate them, right? Now, my last words. Random forest is just a forest, a collection of trees. Okay. In random forest, I have a collection of trees. And as you see, random forest is a bagging model. Is a model average, is an ensemble model, right? I have a bunch of trees. According to our analysis, we just said the trees must be uncorrelated, very different. Otherwise, if the trees are similar to each other, it's like using one tree. Not that. So the trees need to be different. As a result, random forest selects trees in this way. For training each tree, it samples bootstraps first. But if you use the bootstraps, the trees might be still correlated. For them to be very uncorrelated, it also samples from the features. So it samples from the data points. Also, it samples randomly from the features, and then it gives it to a tree. For the next tree, it samples from data points and samples from the features, gives this to another tree. Then, as a result, the variance of estimation of random forest is much less than variance of estimation of one tree. You see the beauty. Okay, thank you very much. We will go over this briefly in the next lecture, start of next lecture.
Sorry, I entered in my last class.
Yes, let me finish this.